I'm Paula Izquierdo. I am a postdoctoral research fellow at the University of Warwick, and I'm currently working with Boris Gansky. And today I am going to talk about systematic uncertainties in the characterization of DBA-Z white dwarfs. The photospheric parameters of white dwarfs are usually obtained by means of photometric or spectroscopic analysis. These two techniques do not always lead to consistent parameters, but the discrepancies are more dramatic if we take into account helium-dominated white dwarfs. Here I'm showing you the well-known example of GD362, a metal-polluted white dwarf that was firstly identified as having a hydrogen-dominated photosphere, but ended up having a helium-dominated one. This can partially explain the different results that we can see in the various studies, but we can see how once the chemical composition was settled, DBA-Z, the studies didn't still give consistent parameters. Our question, or the question that may arise, is how reliable are each set of these parameters? Because if we are to believe the quoted uncertainties in these published studies, we can see how none of them, or most of them, are not consistent with each other. We encountered this similar situation in the analysis of GD424, a highly metal-polluted white dwarf with a helium-dominated photosphere with traces of hydrogen. Our first goal, or our initial goal with this study, was to obtain the chemical composition of the likely accrete planetesimal. But while doing so, what we obtained is that our spectroscopic analysis and the 3 photometric analysis that we performed didn't yield the same photospheric parameters. We partially solved this situation by proceeding with a hybrid technique in which we simultaneously feed the spectroscopic and the photometric datasets in order to retrieve just one set of parameters. But we still remain concerned about the likely high systematic uncertainties that we might be overseeing. With this context and with this in mind, we set our next goal, which was to obtain realistic uncertainties in the characterization of metal-polluted white dwarfs. In order to do so, we obtained a sample of 13 DBA-Z white dwarfs, and we performed several analyses to each of these white dwarfs. In particular, we performed up to 3 spectroscopic analyses with X-Suter, Bose, and SDSS spectra. We did the same in the photometric part, so we retrieve archival photometry from Sloan Pan stars and Gaia DR3, and then we perform this individual analysis to each of the 13 DBA-Z white dwarfs, but changing the chemical composition of the synthetic models. So we tested for pure helium models, which are the DB, helium models plus hydrogen, DBA, and helium models plus traces of hydrogen and metals, DBA-Z. In this plot, we have the probability distributions in the surface gravity effective temperature plane that we obtain for all the individual analyses performed to 2 stars of our sample, where the pink markers display the previous results reported in the literature for 2 of our stars. Now I am going to show you the results. I am going to start with those obtained for the spectroscopic analysis, so the different photospheric parameters that we obtain by fitting X-Suter spectra, which are going to be labeled as diamonds, the Sloan spectra, the Sloan photospheric parameters fitting Sloan spectra as pentagons, and the Bose spectra as stars. The error bars that are displayed are the statistical uncertainties. And what we obtain is that in all the cases, the statistical uncertainties are much smaller than the systematic ones, which we derive by means of the mean absolute differences in the spectroscopic results. That's how we obtain these numbers, these figures that I am showing you in this table on the right, and that we suggest to quote if we just have one set of spectroscopic data. Yeah, one set of spectroscopic data. Then we did the same for the photometric analysis. In this case, the Gaia DR3 photospheric parameters in the surface gravity versus effective temperature are going to be shown with displayed with squares, the Sloan photometry with circles, and the inverted triangles are going to mark the pan-stars photometric results. For clarity, in this plot, I am just displaying the Gaia statistical uncertainties. And again, similar as in the previous analysis, what we obtain is that the statistical uncertainties are much smaller than the systematic ones. In this case, for this analysis, we retrieved two different sets of systematics. The ones that we suggest to employ when fitting Sloan or pan-stars photometry, because what we obtain is that these two sets are much closer. The results that we obtain are much closer than those derived with Gaia. That's why the systematic uncertainties, if we just use Gaia DR3 photometry, are bigger and are the ones shown in the bottom panel. Now we move to the analysis with a different synthetic composition. Why this analysis? Because I think I forgot to mention that. Because we can encounter a situation where we don't have enough signal-to-noise ratio or spectral coverage to completely identify all the elements that compose the photosphere of a white dwarf, and thus we might proceed with an analysis taking into account synthetic models that do not take into account the whole complexity. In this case, I am showing you the spectroscopic results. For this plot is fitting the exoteric spectra, and the pure helium results are marked with crosses. The circles mark the DBA, and the end or beginning of the arrow, the DBA set results. What we obtain is that the inclusion of hydrogen in the models translated in an overall drop of the effective temperature and a slight increase of the surface gravity. While, on the other hand, the inclusion of metals didn't translate in an overall change of these two parameters. I forgot to mention also that the metals included in the models for each of the stars was individually calculated, individually measured for each star, and then we implemented or put those metal abundances in each of the models. If we do the same, but with photometric data, in this case, I am showing you the results obtained for the SDSS photometry. What we obtain is that the inclusion of hydrogen in the models translated in an overall drop of the effective temperature and surface gravity, while the inclusion of metals, on the other hand, translated in an overall increase of these two parameters. Finally, if we want to compare how alike are the photometric and spectroscopic results, I am going to show you that now, and the photometric results are those obtained by fitting simultaneously the Sloan and pan-stars photometry, while the rest of the markers are going to show the spectroscopic results. What we obtain in general is that the spectroscopy yields to much higher effective temperatures and surface gravity. This is in general if we take into account the whole sample. But if we just take a subsample, let's say those stars with effective temperatures retrieved from photometry higher than 15,000 kelvins, we see how this discrepancy between the spectroscopic and photometric results is considerably decreased. Why this cut? Because we know that there are still issues with the implementation of the van der Waals and resonant broadening mechanisms, which dominate below 15,000 kelvins. And this can cause a not so reliable or a bit dubious shape of the absorption lines.
Paula, you've got 3 minutes.
Okay, I am done because I am with the conclusions. So what I want you to take home is that the systematic uncertainties are quite large and we need to start taking them into account because we have been quoting just the statistical uncertainties. And if we are in the field, we know that maybe those uncertainties are not so reliable, but people outside our field might be believing our uncertainties. So if we are able to do it, just perform some systematic analysis. If not, you can quote these numbers. The second thing is that I think we agree that it's time to start looking for a technique to reconcile the spectroscopic and photometric analysis because we have hundreds of examples where these two techniques are not consistent and we are talking about the same white dwarf, so something's going on around there. And finally, that the systematic uncertainties are going to propagate into the derived planetesimal compositions that we are publishing. So we should expect bigger uncertainties there too. And that's all. Thank you.
Thank you very much, Paula.
Hi, Paula. Alejandra here. Can you go back to the plot where you show the effective temperatures? You had a plot with effective log G effective temperature. Actually, my question was, do you have any pulsating white dwarfs there? Because you can also compare, I don't know if it's going to improve or not, but you can also compare the effective temperature and log G that you get from astroseismology.
I don't know too much about pulsating white dwarfs, but I believe the pulsating strip in dBs is around 22,000 kelvins, I believe, and my sample is cooler, so maybe not. It's something that I haven't thought, but I would say no. I don't have pulsating white dwarfs, but I'm here to learn more about it.
Hi, Paula, it's Ingrid here. The difference between the parameters you get from X-shooter balls and SDSS is quite striking. Do you have any idea what's behind that? If it's spectral resolution, wavelength coverage, a bit of everything?
I would say it's a bit of everything. Like we have several sources of systematics there. I would say that the signal to noise ratio can play an important role, but since we are convoluting with the different resolutions, that can counterpart a bit. I mean, if we are talking about, because I haven't shown any plots with the hydrogen to helium abundance, that's another parameter that we take into account in our analysis, and I would say the signal to noise ratio or spectral coverage, because we might be losing some important lines in some of the spectroscopic data sets might also play a role, but we don't know the reasons why we are getting so different parameters.
Hi, Paula. Nicola here. I was intrigued by seeing that adding the metals doesn't seem to have an effect for the spectroscopic parameters, but it does instead have an effect for the photometric parameters. And naively, I would have assumed that it would affect, I don't know, broadening or something, particularly in the uncertainties due to neutral helium broadening. So could you tell us more about why it seems to affect the photometry, but not the spectroscopy, adding the metals?
Okay. First of all, I wouldn't say that we don't see a change. I mean, if we take into account the 13 dBA set, we don't see a significant change in the photospheric parameters. But if we have to take into account that we are dealing with highly metal polluted white dwarfs and those that are not so much polluted. That's why in the overall, we don't see an important or a significant change. But if you go, like the highest metal polluted white dwarfs, we can see a change, for example, for this. Can you see my screen?
Yes.
Yeah. Okay. Yeah. Like, for example, for 0958, this in yellow, we can see a significant change between the dBA and dBA set analysis. Why there's a biggest change in the photometry? I would say that the inclusion of metals with all the free electrons and all the blanketing that they apply doesn't have a super visual or also computational change in the shape of the helium and hydrogen lines, but we can see a change in the slope in photometry. And I would say photometry is more sensitive to the change of the slope. That's why I assume we see a bigger change, if that makes sense.
Yeah, thanks.
Okay. We don't have any further questions, so thanks, Paula, again.